So, hello everyone. Welcome to week 7 of the nptel course Introduction to Rings and Fields. Uh, in this video, I'm going to explain some sample problems and some theory regarding extension fields that will help you solve the assignment problems and understand the concepts better. Okay, so let's get started. Okay, so the fields I have introduced in last session. I have introduced what fields are and some basic properties about it. So now in this session, I will start the field extensions. So definition. Suppose f is a field, then a field k is said to be an extension of f if f is a subfield of k. Right? Basically, if you have a field f and if you have k such that this relation holds, then this should imply k is extension of a. Basically, a superfield kind of thing. Okay, so I told this in last session also. I'll repeat again. Whenever if k is an extension, k is an extension of f, then k forms a vector space over f. Okay, and now there are two possibilities that the vector space is finite dimensional or infinite dimensional, right? So we define degree of field extension. Okay, definition. Degree of field extension. And what is that? This is the simply dimension of the vector space k over f. So formally, let k be an extension field of f. Then degree of k over f denoted by square bracket k, uh, then semicolon f, colon, sorry, and is the dimension of vector space k over f, right? So this is basically degree. So if the vector space is finite dimension, you get the finite number. If the vector is infinite dimension, you said the degree is infinite. Okay. So and whenever the degree is finite, we call the k as finite field extension. Okay. So let's see some examples. Number one, if you take a field, let f be a field, and take k as itself, k as f. Okay. K as f. Then K is a vector space. Of course, every field is a vector space over itself. So what will be the dimension? Dimension of a field over itself is 1, right? I mean, the identity one element will be a basis, right? Then you know dimension of f over f is 1, which implies f is a finite extension. This is a very trivial thing, but just an example. F is a finite extension of f. I mean, there's no much sense in this, but still. The second example is the one useful, the field of complex numbers. So you know that field complex numbers contains R, reals, both are fields, right? So now is the extension. Now we can say C is an extension of R. So question is it finite or infinite? So as you know that every complex number can be written as in the span of so 1 comma I, right? Real span. So if A plus for any or I can directly write Cn is set of all A plus IB, right? Where A comma B belongs to reals, right? So in vector space notation, this is simply what span of 1 comma I, right? This is like A times 1 plus I times B. That's all. Right? So over R, Cn can be written as span of 1 comma I, and this 1 and I are linearly independent, right? Because if A plus IB is 0, then you have only one solution, A equals to 0 and B equals to 0, right? So this means dimensions of Cn, oh not Cn, sorry, C. Dimensions of C over R is 2. Okay. So complex numbers is a finite extension of real numbers. Okay, which is of degree 2. In fact. Then move on to the next example. Third, Q. If you consider Q to the field of rational numbers and take the extension as Q over root 2, which is set of all A plus B root 2, where A comma B belongs to rationals. This is a field you can easily verify, and this contains your rationals, right? So what is this? Is it finite? Okay, so yeah. So this is finite field or infinite? I mean finite extension or infinite extension. So is it this? See, for from the structure itself, you can see this is simply span of 1 comma root 2, right? Over span is taken over rationals, okay, not over reals in this case. Hence, in this case, and this 1 and root 2 are linearly independent elements in q root 2 over q. This implies degree of q root 2 over q is also 2. So it's also a finite extension. Similarly, you can see so many extensions q over root 2 comma root 3 and so on. Okay, so let's see one question about the finite extension. So the question is about like transitivities of finite extensions. So if you have a thing that f k extends f and then you have l extends k, right? So naturally l extends f also, and if you have l over k is finite extension and k over f is finite extension, then do you have l over f as a finite extension? That's the question. So the answer is yes. So if I write it precisely, if L is a finite extension of K, and if K is a finite extension of f. Okay, so you have L extension of K extension of f. Then L is a prove that L is a finite extension of f, and you can say further about degree of f L over f. Okay, so degree of L over f is the product degree of L over K times degree of K over f. So this is what we have to prove. Prove. Okay. So what do we want to prove? That the vector space L over f is finite dimensional, right? So basically we will give a basis for this. So L over K is finite, let's say M. Okay, take, so because it's a finite dimensional vector space, there exists a finite basis, right? So I'll take a basis. Let alpha 1, alpha 2 up to alpha m, okay, be a basis of L. And okay, also I'll say degree of K over f, let's assume to be n, and I can take basis over there also, beta 1, beta 2 up to, okay, this maybe alpha and beta is are not nice notation because they are generally taken for scalars. We are taking it for vectors, so let's change u1, u2 up to um, and then here I take, let's say, v1, v2, vn, be a basis of K over f. Okay, this is important. Here also it's a basis over K. Okay, so how will we proceed? So I have a basis. I will write. How would I copy? Okay, let's start. U1, U2 up to UM. This is basis of L over K, right? And then V1, V2, Vn is basis of K over F. Now, then there is some system problem. Let me see. I hope it should be fine. Yeah. So these are the bases respect to L, K and K over F. So since K is the subset of L, right? So this implies this all elements V1 through Vn, this all belongs to, I mean, these are subset of L again. Now if I consider the new set, let's say U1 through Um, this I'll just multiply. Like say for example V1 U1 V1 U2 will go until V1 then V2 U1 V2 U2 similarly. Okay, I'll proceed. So like if I want to write this is Vi Uj, where I comma j runs from no, I will run from 1 through n and j will run from 1 through m, right? So how many elements are there here? In script B, you have mn elements, right? My claim will be to show that the script B is a basis for K over F because L over F, because L is a extension of K, right? This implies naturally every Vi Uj will belongs to L, right? It's a vector space. So the claim is script B is the basis of L over F. Okay, how would we show this? Okay, so let's take, first of all, let's show it as a spanning set and then we'll show that it is independent. So take any element, let's say y belongs to L, which implies y can be written as summation some alpha i's time ui, right, where ui was a basis of L over K, and these alpha i's are now belongs to K, right, I going from 1 through m, right. But now each alpha I is an element of K. That means for each alpha I can be written as, let's say, beta, how do I write? Beta ij vj, right? J going, not a nice notation. Okay, just change here to be j, change here to be I. Vj. Okay, vi. This one is. Okay, so now this is the representation. This is happening for every I, for each I, right? Because alpha I are in K, so this beta ij's will belongs to F, right? Because K is a vector space of finite dimension over F, right? This is happening for each. Now this is going to put J, for each J from 1 to M. Okay. Now, if I resubstitute there, what do I get? Y is summation J going from 1 to M. Each alpha J is summation beta ij vi and then uj, right? So if I expand this, this is summation beta ij vi uj, right? This is what you wanted, right? So every element, so I mean this summation is, I mean, nothing but just a single summation you can put, because there are two indices. So every element, every y belongs to L has a representation like this, right? This means the script B spans L, right? At least this we know. So now the question is it independent? Now let you take a linear combination and equate it to 0. Okay. Let summation Fij ui vj vi uj, it's commutative anyway, so it doesn't matter, but still vi uj equals to 0. Or what this implies? This implies summation of summation Fij vi, let's say, and then you have uj here, which is 0. But now uj is the basis. This implies this scalar has to be 0, which implies Fij vi are 0 for every I mean for every j basically. Here you go sum from 1 to n. This will imply Fij equals to 0 for every I and for every j. But then this will imply this is done, right? This implies the set of all vi uj is linearly independent. Right? That's all. That's what we wanted, right? This implies that script B you started with is a basis of L over F. So then this implies dimension of L over F is equals to Mn. And what is Mn? M is dimension of L over K, then N is dimension of K over F. So it's a finite dimensional vector space. Further, we have this equality, the relation between the subfields, right? Okay, so this whole property is also called as transitivity of finite extensions. Okay. Okay. And I hope this is clear. Let's go for the next question. So I mean, naturally from this you can say whenever there is a subfield K, then dimension of K over F divides dimension of L over F, right? Because from this expression, right? Dimension of K over F divides dimension of L over F, right? And whenever you take a subfield, because it will be again a vector space, right? And dimension of okay, I'll just write a proposition instead of saying if L is a finite extension of F, and if K is a subfield of L which contains F, then dimension of K over F divides dimension of L over F. Okay, so this is like L you have, F you have. If there exists a K in between, okay, then this relation will be the dimension of K over F divides dimension of L over F. Okay, so this will follow from the last proof that we did directly, but this is an interesting observation because so many times the questions arise like this. Let's say you have a question uh, L, let L be an extension of F with degree 7. Does there exist a subfield K of L containing F such that no such that's all. Does there exist K of K uh, proper subfield containing LF properly? Like what I'm asking here is you have F, you have L. Let's say this with degree 7. Then do you have K which is properly contained here and properly contains here? But this is not possible because if contains then degree will divide 7, right? And it's a proper divisor of 7. But this is not possible, right? 7 is a prime number. Hence the answer will be no. So this kind of questions are tricky question based on some theorems. This will be there for your interviews, for PhD interviews, for Viva exam. So keep an eye on this kind of theorem and questions. Okay. Here's one thing. So if you observe, say how does C over F look like? First of all, A plus IB, right? Where A comma B belongs to R, right? So basically, what is it? You're taking an element I from complex numbers and just writing it in this form, right? A polynomial in I of degree 2, basically, right? A polynomial in I over R of degree 2. That is all of the C. Hmm? So this is a special structure. Okay, this is not arbitrarily you get C. This is a special structure, and now we will investigate about this kind of structure. So what is this structure? Okay, so there is something called field adjunction. So what is this? Suppose K is an extension of F. Take A belongs to K minus F. You take an element. I mean minus not needed. Let's say A belongs to K. Then define F of A to be set of all polynomials in A. Okay, so how do I write it? P of A divided by Q of A, where Px comma Qx, or let's say P comma Q belongs to F over X, and Q of A is non-zero. Okay, so this is the thing. Since K is a field, these values will be there, right? P of A will be some value in K, and because it's a polynomial in K over X also, because K contains F, that's why. So FA is well defined. It is easy to see that this FA will be a field, okay, and which is a kind of a smallest field containing both F and the element K, okay. So we can observe that F is contained in FA is contained in K. Okay? This is a field itself, it is always in between F and K. Okay. So yeah. So here you can observe, right, again for this theorem, similar question can arise like prove that for any finite extension L, you can show this L is exactly equals to F of some A, right? For any A belongs to L, right, which is not in F, because then FA will be a subfield, right? If it is not same, it is a proper subfield, but then you don't have a proper subfield, right? Hence L has to be equals to F of A. So this is a observation that we did later on. This is coming from here. Okay? This cannot happen. That's what I was saying. Okay. So now, yeah. So this is called a field adjunction with A. Okay. So what is it? So from here now we define definition. Simple field extension. What is this? The extension K of a field is called as okay. The extension K of a field F is called simple extension if the field K is F of A, okay, for some A belongs to K. Okay, so like for example, complex number. That complex number is simply R over A, right? If you can see, right? I mean that has to be proved later, but I mean F of A has the structure P upon Q, right? You can take Q as constant one, then you get complex numbers, right? R in R of I. So you can now say that any finite extension of prime degree is a simple extension. Yes, right. Okay, so this is a definition. Yeah. Now, yes. So now we'll see what are the algebraic elements are. Okay. So the whole idea about these extensions, field extensions, and degrees is about observing what happens with complex numbers and real numbers, right? So you take a polynomial, let's say x squared plus 1, right? This is a polynomial in R over x, right? Does not have roots, right? But has but does have root in C, right? Which is I and minus I, you know. So something about this we observe and we want to extend it further for any general field. And what is it called? Algebraic element. Okay, so this is the definition of an algebraic element. So let K be an extension of a field F, an element A belongs to K is said to be algebraic over F if, when do you say an element in the extension algebraic over a field if there exists a polynomial, there will be, okay, this is the nice notation. So if there exists a non-zero, yeah, non-zero, a non-zero polynomial P in fx such that P of A should be 0. Right? So basically, A has to be root of a polynomial in fx. Then you call that element as algebraic element. Okay. Another definition is transcendental element. So basically, the element which is not algebraic. That's all. Not algebraic. Okay. So these are the definitions. So what are the relation of these algebraic elements with the field extensions? The relation is that degree of a field extension is same as the degree of the least degree polynomial for which that element is algebraic. Okay, I mean, for an algebraic extension. Okay. Okay, so now I have to give some more definitions. Pardon me for too many definitions, but they're required for the today's session. So now we have observed what do you mean by algebraic element. I'll just give example. Let's say example. Take k equals to c over r, right? C is extension over R. You know everything. Degree of C over R is 2. It's a finite extension. So I belongs to C is an algebraic element. Okay. Further, you will see every element is algebraic element, because that's what happens. Every finite extension is algebraic. That we will see later. This is first example. Another example is, let's say, q over root 2. Right? This is a field containing q, and you know degree of q over root 2 over q is 2. Huh? So what is the algebraic element? Right? So root 2. See, if you see x squared minus 2, this is a polynomial in q over x. It does not have roots, right? Q, but root 2 squared is 2, implies this polynomial, I'll call this px. P of root 2 is 0, which implies root 2 is an algebraic element. Okay, let's take another question now. Uh, yeah, okay. Okay. So you consider R to be the extension field of Q. Okay, it's not a finite extension. Yeah, that also, that is the question. You try to prove that the reals is not a finite extension of Q. Okay, I mean, that is, real as a vector space considered over field Q is infinite dimensional, basically. That's what it means. Okay, so let R subset of Q then show that root 2 and root 3 are algebraic over Q, and find polynomial Px belongs to Q over X such that P at root 2 plus root 3 now I want to be 0. Yeah? So, okay, root 2 and root 3 and root 2 plus root 3 I want to show. This is also algebraic. Right? So this is my first question, let's say. My second question is, show that Q over root 2 comma root 3, this is adjuncting two elements now at a time. Okay, Q root 2 over root 3. It's same as Q over root 2 plus root 3. Okay, this I have to show. Third question is, what is degree of root 2 plus root 3 over Q? Okay, this means basically degree of Q over root 2 plus root 3 as a vector space over Q. Dimensions. Answer. Okay, so root 2 and root 3. Yeah, so take the polynomials x squared minus 2 belongs to Qx, which implies root 2 is algebraic, and x squared minus 3 belongs to Qx, which implies root 3 is algebraic. Okay, this is easy. What about their sums? So if you take root 2 plus root 3 as, let's say, theta, what is it squared? It is 2 plus 2 times 2 root 2 times root 3, right, plus 3. So what is this? 5 plus 2 times root 6 is theta squared. So if I do theta raised to 4, I'm squaring this thing, then I get 5 squared 25 plus 2 to the 4, 4 times 5 20 times root 6. Right? Is it? I hope this is correct. 20 times root 6 plus then square of this thing 2 root 6, which is 4 times root 6, 4 times 6, 24. 4 times 6, which is, this is 24, right? I'll just write 24. Which is 49 plus 20 root 6. So we can do something. Theta raised to 4. So what happens if I do theta raised to 4 minus 20, 10 times, if I multiply it's 50, right? Minus 10 times theta squared. So what do I left with? I left with 40, 20, 20 get cancelled, then 50 minus 1 plus 1 if I do. Right? So I'll get here theta raised to 4 is 49 plus 20 root 6 minus 10 times theta square is 50 minus 20 root 6 and then plus 1. But as you can see, this gets cancelled, 49 plus 150, and this gets cancelled, everything boils down to 0. Yes. Hence, of the polynomial px as x raised to 4 minus 10x plus 1. This clearly is a polynomial in qx, and p at root 2 plus root 3 belongs to, not belongs to, is 0, which implies the element root 2 plus root 3 is algebraic. Yeah. So one can ask now, what happened earlier? We knew that root 2 is algebraic and root 3 is algebraic, and then what turned out is root 2 plus root 3 is also algebraic. So is it always the case? I mean, if I take any algebraic element A, any algebraic element B, then is A plus B is also algebraic? Then is AB is also algebraic, or A by B is algebraic? So our answer to all these questions is yes. If K is an extension of a field F, you collect all the algebraic elements over F in K, then that also forms a subfield. Okay, that's a field in between F and K. Okay, so well, this is a result that we'll see after some time. Okay, right now, yeah. So we have now we'll define something else. So I gave a question in between bunch of definitions. Okay. So I have defined what an algebraic element is. Now, yeah, also what is the degree? I have defined degree also. Degree of an algebraic element um, suppose is an algebraic element over L, then degree of A over F is the degree of the uh, so basically it's a degree of a least degree polynomial. Okay, how to write this then? Say is n if if a is a root of n degree polynomial in fx and no other polynomial of less degree. Okay, so for example, take element root 2. Root 2 belongs to q over root 2. Okay, so root 2 is algebraic, right? So you take the polynomial x square minus 2, then you know that p of root 2 is 0. So this is a 2 degree polynomial where root 2 is a root, right? But do you get any 1 degree polynomial where root 2 is a root? No, right? Because 1 degree polynomial has to be x plus or minus a. But if there is a root, then x has to be equals to root a, right? But then see, you take any 1 degree polynomial, it will be like x plus a, belongs to qx, and if root 2 plus a is 0, then you get a equals to minus root 2 belongs to q. But this is contradiction, right? Hence, degree of root 2 over q is 2, because 2 is the least degree polynomial satisfied by the element root 2, and this x square minus 2 is the least degree polynomial. Just give me a minute. Okay, so this is the example of degree of extension. Now, what are those fields for which every element is uh, the algebraic element? What are those extensions? So those extensions are called as algebraic extensions. So that's a definition. The extension k of f is called an algebraic extension if every element is algebraic over f. So what's the definition? If every element is algebraic, then the field extension is called as algebraic extension. Okay. Okay. So now we'll see like what examples do we have of algebraic extensions. Okay. So what we'll prove now next is the following theorem. Every finite extension is algebraic. Okay, this is what we're going to prove. Show that every finite extension of a field is algebraic. Okay, proof. Suppose K is an extension of F. I mean finite, I'll take. Suppose K is a finite extension of F. So when will K be an algebraic element? If every element is algebraic. When will K be an algebraic extension? If every element is algebraic. So what do you know? Then K will be an algebraic extension if uh, every element is algebraic. That means we have to find a polynomial over F satisfied by this element A, every element basically. You take any arbitrary element A, then we need a polynomial. Okay. So now what you do is you take any element that A belongs to K, be any arbitrary element. Consider this set. Set of all you take, let's say 1 A squared up to let's say A raised to n. Okay, assume also that dimension of K over F is extension is n. So the extension is let's say finite extension, no? So n degree extension. Now how many elements do you have here? We have n plus 1 elements. Then what do we know? Any set of in a finite dimensional vector space, any set of cardinality n plus 1 is linearly dependent, right? Where n is the dimension. So this implies C is linearly dependent, that is there exist scalars alpha naught alpha 1 up to alpha n belongs to the field F such that alpha naught 1 plus alpha 1 a plus up to alpha n a power n is 0. I mean, all scalars such that not all alpha i's are 0, that all, I mean if all is 0 then of course this expression on the left hand side is 0, right? But you get a scalars which are not all 0, but even though the expression on left hand side will be 0. This is what linear dependency means. Then what do you know? If you consider now the polynomial px equals to alpha naught plus alpha 1 x plus up to alpha n x power n, this is a polynomial in fx, right? Because the scalars are in the field F and P of that element A is 0. So you find a polynomial in Fx such that P of A is 0, right? Which implies the element A is algebraic. But the A that we started with was arbitrary, right? Hence every element is algebraic. And degree is also at most n, right, for every element. So every element in K is algebraic over F, hence K is an algebraic extension of F. That's all. Okay, so I hope this is clear. Okay, so I have already seen that, told you that for any A and B which are algebraic, you take A plus B, that will be algebraic, A minus B algebraic, product is also algebraic, and division will also be an algebraic element, right? So we'll see that theorem now. Theorem that K be an extension of a field F, then elements in K which are algebraic over F form a subfield of K. In other words, if A comma B belongs to K are algebraic, then A plus minus B product and A by B, I mean, of course here you have to assume B non-zero, are algebraic. Okay, let's see the proof. So see, this theorem will also be used in a different way. For example, if um, I want to say that every complex number is algebraic over real, right? How would I say that? So now, I mean, from the before theorem, it follows directly that because it's a finite extension, hence it's algebraic. But using this theorem also, you take any uh, uh, okay, so you collect all algebraic elements in complex number. You take all algebraic complex numbers, and then the collection is a subfield, right? It's a subfield of C, and it's a proper subfield, of course. So that means it has to be in between R and C, but there is no subfield, right? There is no field in between R and C, because what will be the degree? If it is 1, then it is R. If it is 2, then it is complex. That means then it proves, right? Every complex number will be algebraic. Okay, it's a complicated proof. I mean, you have a simpler proof, right? It is finite extension, hence algebraic. So no need. Let's prove this theorem. Suppose A and B belongs to K are algebraic. Okay, since B is algebraic, there is therefore it is also algebraic over FA. Okay, now FA is a superfield, right? Since B is algebraic over F, what do you have is B is algebraic over FA, right? I mean, what do you mean by that? So there exists a polynomial in FA of X such that this is 0, right? But FA contains F, so there is no much significance of the statement, but okay, we can say that B is algebraic over FA also. Note that any non-zero polynomial over F is also a non-zero polynomial over FA. Yeah, because of this we have the previous statement. Okay. Now B is algebraic over FA. What does it imply? Right? Implies FAB, right, is a finite extension, right, of FA. Okay. I think to prove this we need a lemma which was not proved earlier. Yeah. So the lemma is basically for any extension, an element is algebraic if and only if it's is, you consider FA, that has to be finite extension. Okay. So yeah, that part is missing. Okay, so maybe this proof I'll cover in the next session because it is involved. It needs some different lemmas. So you cannot prove it directly. Okay, so session. Okay. So this theorem I will prove in the next session, but it is an important theorem that if you collect all algebraic elements, it will form a field. Okay. So one easy exercise for you guys can be this. Do that. Ah, okay, now I will prove this. Prove that uh, R is not algebraic extension of Q. Proof. So how will you prove this? So what I will do is I will prove that collection of all algebraic elements in R over Q is countable. Okay, so if I am able to show that the collection of all algebraic elements is countable, then it cannot be whole R, right? Because R is uncountable. So that will be my proof. So let I will name S a set of all A belongs to R such that A is algebraic over Q. Okay. So what is my claim? My claim is that S is countable. Okay. So how would I prove this? See, any polynomial, if there exists any algebraic element, is it corresponds to a polynomial, right? In fx, in qx, right? So there will be as many algebraic elements. So number of algebraic elements will always be less equal number of polynomials, right? Number of polynomials. So, okay, how would I show this? I will give a mapping, let's say. How can I give this mapping? Okay, I'll prove this in a different way. Let's say I'll now consider mm, okay, let's say I'll write P1 is my set of all 1 degree polynomials. Okay, I'll write this. Pi is the collection of I degree polynomials in QX. Okay, then and Ri will be set of all algebraic elements in R of degree I. Okay, so now I can do some one relation. So every element in Ri has a polynomial in Pi, right? A pair, a kind of pair. Okay, I mean there will be so many elements in Ri which have a same element in Pi. That can be possible, but accountably many, not more, because every polynomial has degree n, right? At most. I mean every polynomial of degree I has at most I roots, right? So now what I'll do is, how many PIs can you form? I mean, what is the cardinality of PI, right? So as you know that any polynomial, the cardinality of Pi is countable, right? The cardinality of Pi is countable. This implies if I take uh, so what is Qx? Basically, Qx will be then union of Pi's, right? I going from 1 to infinity, right? This implies Qx itself is countable. Right? Qx is countable. Set of all polynomials with rational coefficient is itself countable. Then what are all the rational? What are the algebraic elements? Right? Each algebraic elements corresponds to some polynomial. Right? So if the whole Qx is countable, then set of all algebraic elements also has to be countable. Right? Every polynomial has some finitely many roots. So I'll just give a function, a mapping. I'm just looking for a mapping to prove everything. Uh, if I give a mapping phi from S to Qx, or I'll not S, I'll do mapping S tilde. What is S tilde? S tilde will be now, okay, collection of roots AI such that A is algebraic and they correspond to the same polynomial. Basically there exists some the collection of A1 A2 up to AI such that P of AI such that there exists a polynomial P belongs to what Pi, right? Pi such that P of A uh, j equals to 0 for all 1 less equal j less equal I. So a collection of all these kind of sets, collection of all AIs. This is my S tilde. Okay. So now what I'll do is I'll map this set A1 up through AI to the polynomial Px. Right? Yeah. So yeah, this is a perfect mapping. This is a 1-1 mapping, you can verify. And this is a 1-1 mapping. Also onto, right? Every not onto, sorry. This is a 1-1 map. Every rational number does not have root, but those who has root can be written like this, which implies cardinality of S tilde, right, is a less equal cardinality of Qx, which is countable. Now, since you are collecting finitely many from S itself, this implies S is also countable. So what you have showed is for any, if you, so what you have showed is collection of all algebraic elements in R over Q is countable, but R itself is uncountable, right? Which implies R cannot be same as S, which implies R is not algebraic extension of Q. Okay. Yeah. So yeah, we have shown that R is not algebraic extension of Q. So now let's go further. Let's show the next theorem. No, next question I have. Let F be a field. Let F be a field and F X be the ring of polynomials in X over F. Let Gx be a polynomial in Fx, and now you consider an ideal generated by Gx. Right? Okay. Prove that Fx quotient V is an n-dimensional vector space over F. So yeah, what is the significance of this F? This Gx is n degree polynomial. Okay, so this is what we want to prove. Okay, I'll take this to the next page maybe. Okay, so we want to show, so not written properly. We want to show that fx quotient v is n degree polynomial, is a n dimensional subspace. Okay, first of all, what is your v? V is set of all fx gx, right? This is the ideal generated by gx that we know. F belongs to f over x, right? So fx quotient by v, how you define this is collection of all polynomials, and basically fx plus cosets, right? Collection of all cosets. Don't confuse with this f and this f. You think like this are same, but this is just a representative, right? We use as a notation, right? So what are the additions and all defined on this? That we know one defined addition as follows: fx plus v plus, let's say, not g now, let's say f1, f2x plus v is defined as f1 plus f2, right? I mean f1x plus f2x plus v is a coset with this element. Also, we define scalar multiplication as f1x plus v. If you multiply by any now element in f, alpha, let's say alpha is the scalar, then alpha f is same as alpha f1x plus v. So these are the operations, addition and scalar multiplication in the ring, in the field, sorry, on the set fx quotient v. I want to show that this is forms a vector space over with these operations. Okay, addition and scalar multiplication. Okay, so first of all, with this addition, as you can see, because the f over x polynomials are abelian, right, with respect to the addition. So clearly, quotient v is abelian group. Back to addition. Now what happens for multiplication? We have to show some commutative laws and all, right? So let's show. First one, take any element a, b belongs to f, and f1, f2 belongs to fx. First one is a plus b times your set v plus, no, we take the left portion. Say f1x plus v, right? So by definition, this is a plus b times f1x plus v. But you know, in fx, this is just a times f1x plus b times f1x plus v, and by the definition, this is a f1x plus v plus b f1x plus v, right? So the multiplication is associative. You can, you know, multiply in between. So this is one property. Now the second property, can you go in the brackets? Yeah, that is a times a of 1x plus v, right, plus f2x plus v. Okay, it has to be different notation. Then what does this means? Okay, so what you know is a times f1x plus f2x plus v, which is we multiply inside a f1x plus a f2x plus v, which is a f1x plus v plus a f2x plus v is nothing but a times f1x plus v plus a times f2x plus 1. So this is also valid. You can take the multiplier inside. The third operation is not operation. Third property you have to verify is AB. Okay, I mean let's say a times b of f1x plus b. What this is? This is a times b f1x plus b, but we same as ab f1x plus b. Okay, so this is also verified. So all are natural properties, so that it will be easily verified, of course. Last property is 1 times the element has to be the same element. Okay, so you get 1 times f1x plus v, but this is simply f1x plus v, right? So because this multiplies with the field element and this is the same. But now using all this property we can conclude that fx quotient out with v is a vector space, right? So what is left to prove that it is finite dimensional indeed. Okay. Now suppose you have the element gx. Okay. Suppose degree of gx is n. Okay. We have to show that degree of fx quotient v as a vector space over no, this is not field extension, this is the proper notation. We show that dimension of fx quotient v over f is n. So what will be the natural choice for basis is this v plus x, v plus 1, v plus x squared until v plus x raised to n minus 1. So what we are claiming is this should form a basis of Vx over f. Okay. So if I call this set as script B, then B is basis. Okay. So what do we have? First of all, we show that this set is independent. Okay. So suppose take the linear combination a naught v plus 1 plus a2 v plus x a1 up until a n minus 1 v plus x raised to n minus 1 is 0. I want to equate, but what is the 0? Here the 0 is v itself, right? Because that's how quotient group is defined. So this implies v plus a naught plus a1x plus until a n minus 1 x raised to n minus 1 equals to v. But this happens if and only if this polynomial belongs to v, but which is generated by gx. So when can this happen? Right? So an n minus 1 degree polynomial belongs to gx, right? But this cannot happen, right? Because gx has degree n, and an n minus 1 degree polynomial cannot belong to ideal generated by gx because this polynomial should divide gx, right? And a degree less polynomial cannot divide gx. So this is not possible. This happens if and only if it has to be constant, right? I mean a zero polynomial, not even constant, a zero polynomial. If and only if this a naught equals to a1 equals to an minus 1 is 0. And because I should write this step in between. Right, and then a degree n minus one polynomial cannot divide a degree n polynomial, right? Unless it is zero. So that's proof. So this implies that the set is linearly dependent. Sorry, independent. Yeah. So we have showed that this set is linearly independent. Now we have to show that this set also spans, okay, the whole vector space. What do we mean by that? Every element can be written in this form. Okay. So how can we write this? You take any polynomial fx belongs to fx. Okay. If degree of fx is strictly less than n, then you take the same alpha and create. Okay. This implies fx equals to, let's say, a naught x plus a1 x, sorry, a naught plus a1 x plus up to a n minus 1 x raised to n minus 1. Then fx plus v is same as a naught times 1 plus v plus a1 times uh, x plus v. See, I am doing 1 plus v or v plus 1 because they are same, right? Sometimes. I mean, I am doing this sometimes because they are same always. Okay. So, elements of degree n minus 1 can be written like this. Suppose it's not. Let now if degree of fx is greater than n, then divide by gx, then what you do is you write fx as some polynomial hx times gx plus rx, right? This is a remainder polynomial where degree of rx is strictly less than n, right? But then what do you get? Fx plus v is same as rx plus v, right? And rx plus v belongs to span of this 1 plus v comma x plus v go on until x raised to n minus 1 plus v. That's all. That means for any f, fx plus v belongs to span of these vectors, right? This implies this set 1 plus v, x plus v and all x raised to n minus 1 plus v spans the vector space fx quotient v. Hence this is the basis. Is a basis of the same fx over f, which implies dimension of v is, how many elements are here from 1 to n minus 1? N. Okay. So I hope everything is clear. So this is done for today. So if you have any doubts, you can ask, or we'll meet on next Tuesday.